Um, yeah. Hi everyone. Welcome to another edition of the ZS Calculus seminar. Today we'll be talking to us about the 2D Quon language. So please, Byungmin, if you want to start.
Okay, thanks everyone for coming and thanks for the kind invitation. I'm very excited to be connected with the GX Calculus community. Uh, to be honest, I'm not very familiar with GX Calculus, so please feel free to ask any questions, any comments. If you have any questions, comments, please feel free to interrupt me between the talk. Okay, so today I'm going to talk about 2D Quon language. I'm from MIT. My name is Byungmin. And this is a joint work with Chun Zhao, Zhongwei Liu, Sun Gao, and Sunon Choi. And you can find more details on the paper. So I would like to motivate the talk by saying that quantum many-byte states are exciting. So it can be used to solve the quantum chemistry problem, the ground state of the interacting Hamiltonian encodes the chemical properties of the given molecules, for example. And then it can be used to solve the optimization problem using quantum circuits and so on. And also is a key to understand the quantum phase of matter. However, is computationally intractable. So the key question I would like to address during this talk is that in the space of quantum tensor network, which contains most of interesting quantum many-body states, that the question I would like to ask is that what is the classically simulable or tractable fragment? And can you further expand the non-tractable classes? Luckily enough, we have an example where we have special cases which are solvable, namely Clifford and Matchgate. So Clifford, as you are pretty familiar with, is a circuit generated by Hadamard, phase gate, and CNOT gate. It has an efficient polynomial classical algorithm, and the key idea is to keep track of the stabilizer instead of the state itself. We keep track of, for example, the trigger state and its stabilizer, how it evolves under the Clifford circuit. Despite that the Clifford circuit is classically simulable, it has a wide application such as designing quantum corrected code and relatively fault-tolerant quantum computing. And the magic state or magic gate to make Clifford circuit universal is the T state and T gate. And my understanding is that using ZS calculus, you can faithfully represent and encode all the Clifford computation. And similarly, there's another classically similar class called Matchgate circuit. You can think of it as a circuit generated by Z rotation and nearest neighbor XX rotation. It also have an efficient algorithm, but key idea is that here you can map the corresponding qubit dynamics into the fermionic dynamics through the Jordan-Wigner transformation. Then the Z and nearest neighbor XX maps to the quadratic in the Majorana operator. So that all you need to do is to keep track of this Gaussian evolution, which is easy to do classically. I should point out that the underlying tractability of the Matchgate circuit is related to the tractability of the weighted planar perfect match planar diamond model. Despite that this is tractable, classically tractable, it has a wide application in solving quantum many-body problems in condensed matter and quantum chemistry problem, and has been routinely used under the name of the Hartree fork. And the magic gate for making matchgate circuit into a universal one is the swap gate, or the next nearest neighbor matchgate. So here the planarity is very important in the matchgate quantum circuit. And once you go outside this planar region to make your tensor network non-planar, then you can utilize that into making a universal computation in a way. And also my understanding is that planar GW calculus can capture the matchgate computation. Oh, any questions or? Okay, so we can move on. So now, given these two classes, Clifford and Matchgate, the modified question that I would like to ask is what is the unifying framework for these tractable classes? And also, given this unifying understanding, can you further expand the tractable classes beyond Matchgate and Clifford? So before going deep into my talk, I should like to point out the parallel independent work by Zhonghui Liu Group. You can find more details on this paper where they looked at the computational complexity in terms of number of magic holes. Then when number of magic holes is zero, which captures Clifford and Matchgate computations, but if you relax that condition, then you can capture more wider range of tractable states, and you can find more details in this paper. So with that, let me start by presenting some outline of my talk. So first, I'm going to introduce 2D Quon diagrams and the universality result of that, and claim that 2D Quon diagrams or 2D Quon language can be used as a unifying framework for tractable classes, namely, it gives a simple diagrammatic characterization of Clifford and gives a simple diagrammatic characterizations of Matchgate. And using that, we can even generalize to something we call punctured Matchgate. And I'm gonna discuss some applications of the 2D Quon diagrams. With that, let me start by introducing 2D Quon diagrams and the universality results. So 2D Quon diagram. The way I view Quon diagram is that it provides some internal structure for tensor network or tensors in the tensor network diagram, which allows some diagrammatic manipulation. So in the usual tensor network diagram, we denote tensor as like this kind of box and some external tensor legs attached to it. And it's sort of like a way to represent some array of numbers in a boxed form. And throughout my talk, I'm going to assume all the tensor network has a tensor leg with bone dimension 2. And Quon diagram, you write an equivalent to tensors, but in a diagrammatic way, which encodes some physical process between involving the braiding and scattering of Majorana zero mode. So I'm gonna be more specific in the later, but for now, you can think of this as, oh, there are 4 black lines, each of which represent the Majorana world line. So here the time direction flows from top to bottom. And here, 4 Majorana lines ending on an open interval is meant to encode 1 qubit. And this diagrammatic rotation encodes some physical process of the Majorana zero mode. But at the same time, it also encodes the tensor components as well. So here it has an open interval where 4 Majorana lines end, and I'm going to use that to encode 1 qubit. So for example, tensor contraction in the usual tensor network diagram can be translated into the gluing of diagrams. So in this case, for example, sorry. So here, if I view this diagram as some quantum process, then on top, we create some quantum state that lives in a 1 qubit state out of vacuum. This upper portion defines a quantum state, and this middle portion defines a map between 1 qubit Hilbert space to the 2 qubit Hilbert space. Because if I look at the cut in the middle, then I have 2 disjoint intervals, each of which 4 Majorana lines end. So each interval meant to encode 1 qubit. Therefore, this middle portion gives a map from the single qubit Hilbert space to the 2 qubit Hilbert space. And the bottom portion is a map between 2 qubit Hilbert space to another 2 qubit Hilbert space. Do you have any questions or?
Byungmin, so
Yeah.
4 lines in a single qubit. This is something special for this Majorana anion? Because I've seen other things where two lines make one qubit.
Yeah, exactly. Yeah, thanks for asking. So the way to view Majorana fermion or Majorana zero mode is the following. So if you have one complex fermion, then you can split into two Majoranas. So if you have four Majoranas, in principle, you can encode two qubits because you can pair up four Majoranas into two complex fermions, and which gives the two qubits. But here I'm gonna encode that one qubit in a parity even subspace generated by these two qubits. So this is the blue shading that I'm denoted here. So in principle, I could have encoded two qubits, but instead I'm using parity even subspace of that. So in turn, I encode one qubit. So same thing happens, for example, here. There are four lines, but I have parity even projection on left one and parity even projection on the right four pairs. So that in total, I encode two qubits out of the
Right.
whatever subspace by those.
So two lines can represent either like, let's say cat 0, cat 1, and then four lines can be 0, 0, 0, 1, 1, 0, 1, 1. But then you're only
Yeah.
taking the even parity subspace of 0, 0, and 1, 1. And so then
Exactly.
again, you have
My
a single qubit.
exactly. My logical 0 and 1 are 0, 0, 1,
Uh,
1. Yeah.
yeah, I see.
Yeah.
Okay.
I'm gonna utilize those kind of like redundancy in encoding in a way.
So sorry,
Yeah.
excuse me. So then you're talking about only fermions, right? There is no anyons or
Uh so so I'm going back and forth. But mainly I'm interested in qubits. So you can think of like why I say Majorana zero mode and complex fermions as it is like complex object, but I'm going to use Jordan-Wegener transformation to make it like a qubit all qubit language.
okay, thank you.
Yeah.
Sorry, I didn't follow how. So I understand you can go from 0 to 0, 0 plus 1, 1. Or, sorry, 0, 0 and 1, 1. But that's only two wires. How are there four lines?
Okay, so each line is not a qubit line, but the Majorana line. So when you should think of like two lines as a result of the fractionalization. So if you pair up these two and these two, then you have two complex fermions, which gives me the physical Hilbert space. But I'm using logical Hilbert space, which is like even parity projection.
So the physical Hilbert space is four-dimensional? Is that
No, four dimension. Yeah, 2 to the 2. Yeah, four
and
dimensional.
each line here is like let's say one element of the four length four
No, oh, no,
vector.
no, no. So each line is like on like fractional division of freedom. You cannot think of this as like on representing one like dimension or whatever. You should pair up these two lines to form a complex fermion, which then gives you valid like uh two qubit degrees of freedom or complex fermion.
Okay.
Yeah. So this is like a fractionalization happening in like condensed matter literature, for example. So if you can in this case, like you can like your for example this Majorana zero mode. This is literally Majorana zero mode where your qubit is not encoded in a 1 0 mode, but you have to pair up another zero mode to make a qubit. Yeah. So let me give a more sorry. Let me give you a more general overview of the Quon diagram, where the Quon diagram, it consists of Majorana diagram plus some background manifold. So Majorana diagram describe how the Majorana zero mode evolves under the time evolution, and the background manifold is the manifold on which Majorana zero mode lives. At the same time, it's meant to keep track of the parity even projection that I explained briefly earlier. So the Majorana diagram is a Majorana world line. It's like a For example, if I think this as a corner process from where time flows from top to bottom, then for example, here in the upper part, I pair create Majorana zero modes. And this dot is a Majorana operator that acts at this particular space and time point. And this data, which I denoted here, is we call something called the scattering or the free fermion evolution between two Majorana modes with some angle data, some continuous parameter data. And this is a braid, which is a special element of scattering, but at special values. But this is important, so I'm gonna keep a separate diagrammatic notation to denote them. And for example, here I can parallel them. So throughout my talk, only scattering and braid play an important role. So let me just highlight that. Yeah. I'm sorry. And there are several diagrammatic rules because of the fact that you're using the Majorana zero mode. For example, the vacuum amplitude, for example, if you create the pair-create and pair-annihilate, then you can simplify the diagram using this unknot simplification rule. We associate the vacuum amplitude to be square root of 2 in this case. And as expected, the braid notation is meant to provide this kind of diagrammatic simplification rule, such as rider-master moves in the knot diagram context. And because Majorana operator satisfies the anti-commutation relationship, it also satisfies, for example, I can pair create or pair annihilate Majoranas. If I change the relative location between dots, and I have to have this minus sign, and dots and braid can interchange on each other, but with sometimes with carry with some like additional phase factors. And you can expand, for example, one diagram, say, scattering in terms of superposition of other diagrams. I don't want to like demand you to remember all these rules. I just want to highlight that, oh, these are diagrammatic notation that has some topological rules with flexibility as in knot diagrams.
Byungmin,
Yeah.
so, a question about this rule that introduced the minus signs when you move these dots past each other on different lines.
Yeah, exactly.
So this means that when you do a rewrite, you need to somehow use global information on your diagram, which you can't. Like to me, like these lines are somehow entangled. That like moving things on different lines creates
Yeah, I would
like
say this. You need to keep track of the relative time ordering.
Right.
So I'm omitting the time like this time direction, but you can think of this time direction is there, and then whenever you simplify, rewrite the diagram, then you have to keep track of that.
So, for instance, I can't really think of this as a monoidal category because it doesn't satisfy this interchange rule where I can slide morphisms past each other on different lines.
So my understanding is that if you have like this background manifold, then you can impose that. But I'm not very familiar with this monoidal category thing, so. But my rough understanding is that if you fully utilize the background manifold, which I haven't introduced yet, but I will introduce in the next slide, then you can sort of promote all this thing into something that satisfies all the categorical interpretation.
And does it make sense to also consider a version where you mod out these global phases? Like, is it like in quantum mechanics where the global phases don't really matter?
That's a good question. But at the same time, let's say you want to evaluate some closed Quon diagram, and your purpose is to get some corner amplitude, which is like a, say, U1 number, then I need to keep track of all these numbers.
Right. But then if you want to create a probability, then you could get rid of them, for instance.
Yeah, in some cases you don't really need to keep track of all these complicated U1 factors. Yeah, I agree.
Thanks.
Yeah, thank you. Thanks for asking. Okay, the background manifold here is like a spacetime manifold on which Majorana modes live. And I'm gonna assume like time flows from top to bottom, but you can also think of this, each space-time point has its own like time coordinate, so you can compare this local uh, or time difference, for example. And this is also meant to impose some parity-even projection over Majoranas. So as I explained briefly earlier, I have four Majoranas which could in principle encode two qubits, but I'm imposing one parity-even projection which results in encoding one qubit. So for example, if I have a hole or genus in the diagram, then along this time slice, I need to impose two separate parity-even projections. And same is true in the boundary. For example, here I have two zero intervals. I need to impose parity-even projections accordingly. So together with Majorana diagram and background manifold, it forms a Quon diagram. For example, I have a following Quon diagram, and I can have because I'm utilizing parity-even projections and so on. I have a further diagram rewriting rules that I can utilize. For example, I have these parallel lines. Then out of vacuum, I can pull out the Majorana dots because I'm utilizing parity-even projection. And for example, if my scattering element is here, I can move to the right using this is the allowed diagram rewriting rules in the Quon diagram. I can even modify the connectivity between background manifold and Majorana diagrams, such as when there's two parallel lines in between, I can reconnect those diagrams. And most importantly, there's something called the string genus relation, where if I have an isolated hole and an isolated Majorana loop that encloses this hole, where this Majorana loop does not scatter or break with the nearby Majorana lines, then I can remove the genus and the Majorana loop altogether using so-called the string genus relationship. And throughout my talk, I'm gonna only use the string genus relation and also just highlighting that because of the fact that I'm utilizing Majorana diagram, background manifold, parity-even projection, and so on and so forth, there are many topological rules with some flexibility that you can utilize. So 2D diagram. So here I'm gonna present some examples that how one can encode the quantum computation using Quon diagram. So as I said, I'm using 4 Majorans to encode 1 qubit. For example, here the Z eigenstate is given by following. Some like I have a pair creations of 4 Majorana modes, and then like it's 0, and the one logical 1 state is given by the same diagram with 2 parallel Majorana dots. And the Pauli operator are given by 4 parallel Majorana line, but with the dots added. For example, X is like this and Z is like this. The one way to see this is that, for example, if I apply X operator on the logical 0 state, then as I said, this tensor contraction amounts to the glooming of diagrams, where the upper part is the 0 state and the lower part is the X state. And if you diagrammatically glue them, then it gives the logical 1 state. And similarly, if I apply logical Z on the logical 0, then it amounts to following diagrammatic concatenation, where you can pair annihilate two Majorana dots, which gives the logical 0 with the plus sign. And if you had applied Z on one state, then you get back to the one state with the relative minus sign because of the fact that those Majorana dots are satisfy the anti-computation relation. And the 1 qubit gates can be encoded as using braids for the Hadamard and phase gate, and then some scattering elements using for the Z rotation. And already this tells me that it's already these choices for the gates are universal for the 1 qubit gates. So which means that if you give me an arbitrary 1 qubit gate, then I can decompose into the element gates generated by these elements. And using the diagrammatic gluings, I can give you back the corresponding Quon diagrammatic representation of the gate that you delivered to me. You can also represent 2-qubit gates using Quon diagrams. And these are meant to chosen so that all the gate set becomes a universal gate set for the quantum computation. So if you give me an arbitrary quantum circuit diagram, n-qubit quantum circuit diagram, then I can decompose into the elementary generating set. And by the substituting each element by a corresponding Quon diagram and using diagrammatic gluing, I can give you back the Quon diagrammatic representation of your quantum circuit. Any question at this point?
So I'm a bit confused about that you have these unitary operations, but they include wires that sort of go back into the past and new wires that get created. So it seems like
Yeah, for example, like
information is
this.
not being passed. Yeah, information is not being passed along. Like
Yeah,
what?
so things that generally these kind of like pair creation, pair annihilation does not give you a unitary quantum gate. But here I'm imposing this parity even constraint and so on, parity even constraint, so that as a result, this diagram happens to be unitary. For generically, I will get the tensor network, tensor that does not have a unitary in general. Okay. Yeah, so here I'm choosing my quantum gates in such a way that these portion forms a Clifford gate, and these portion forms a match gate. So this is already enough to show the universality result of Q1. So any tensor network can be efficiently represented by a Q1 diagram and vice versa. If you give me a tensor network diagram, then I have an efficient algorithm to compile into the Q1 diagram. And if you give me an arbitrary Q1 diagram, 2D Q1 diagram, I can compile back to the usual tensor network diagram. So proof is actually easy, but I'm gonna just guess the proof. So fourth part, given a tensor network diagram, then using the generating set of the Q1 diagrams that I presented earlier, plus some parity even projection, it is universal to represent all the Q1, all the arbitrary tensor network and represent it by a Q1 diagram. And given a Q1 diagram, essentially using diagrammatic parsing, there is an efficient compilation process from a Q1 diagram to the planar tensor network of bone dimension 2 with rank R tensors. So with that, I'm gonna move on to the diagrammatic characterization of Clifford and Matchgate. But before that, do you have any questions?
Actually, I do have a question.
Yes, yes.
So you said that your algorithm is efficient for representing an arbitrary tensor network as a Quon diagram, but wouldn't that depend on on how I've represented my original tensor network diagram? Like if I say I've got this tensor in here and the components of that tensor are like the results of some like number p hard problem.
Yeah, I agree. Yeah, in that case, it cannot be done efficiently. So it has to be done with quotation mark, with some care. So let's say you have some efficient representation of the tensor network diagram. Say you have a like depth polynomial in qubits, and each tensors in the tensor network diagram, you can specify that components efficiently. In that case, I can provide the efficient compilation process to Q1 diagram.
Okay.
But,
Yeah.
but as you said, if tensor or tensor network is a solution of some complicated Sharpie hard problem and so on and so forth, then I don't know how to translate into Q1 diagram.
Okay, thank you.
Yeah, any other questions? Okay, then I'm gonna move on to the diagrammatic characterization Q1. Clifford and Matchgate. So first diagrammatic characterization theorem is that Clifford tensor network can be represented by Quon diagram with only braids and vice versa. For example, given this Quon diagram, I can readily tell that this diagram represents Clifford tensor network because there are no braids appear in the diagram. So this imposes some condition only on the Majorana diagram, or not on the background manifold. So for example, here I have a hole or genus in the diagram, and which does not appear in the Clifford diagrammatic characterization. So proof is actually also easy. So fourth part is that if you give me a Clifford tensor network, then since it's a Clifford, it is generated by the Clifford generating set. And all the generating set that I presented to you earlier does not have a scattering element in the diagram. And if you do the tensor contraction, which is merely gluing up diagrams, that does not also introduce additional scattering element in the diagram. So you can show that any Clifford tensor network has a Quon diagrammatic representation without any scattering element. And the backward part is also easy. So given a Quon diagram with only braids, then you can do diagrammatic parsing to represent it as a Clifford tensor network. Any questions? Or yeah, then I'm gonna move on to
Sorry, how
you
is
have
the
question?
other
Yeah, yeah.
direction easy? So given a Quon diagram with only braids, how do you get a Clifford circuit out of it? Clifford diagram out of it?
So essentially, you do the diagrammatic parsing. So you make a quartet of Majoranas and identify each part of the diagram using this dictionary and correctly identify as for example, oh, I have 4 parallel lines with 2 dots here, then oh, must be an X gate. So I replace that particular diagram part into the X tensor and so on and so forth.
But how do you know that you can't get a diagram how do you know that for any diagram you can do this parsing?
I can always group the quartet of Majoranas. So using the string genus relationship, actually, so my diagrammatic representation is kind of simple. You only have braid, dots, or scattering. Or in this case, you don't have scattering at all. So you only need to identify where the braid occurs and where the dots appear, and just finding the corresponding elements in the dictionary that I presented to you.
I guess it's not obvious to me that the Clifford generating set would give you all diagrams with that can be constructed with braids and dots. Like it's easy to see that given a Clifford diagram, it is going to be a diagram of which has only braids and dots, but it does not look obvious that all diagrams like those
Yeah. So
reach
maybe
from.
I could have presented all the diagrams that consist, for example, like braid appear only here or braid appear like so here like braid appear in the middle of the diagram, but I could have presented a diagram where braid appear only here, which is a composition of like Hadamard and phase gate actually. But it can be done. I just didn't present all the generating set, but you can always do that. And those diagrams are all generated by the combinations of those diagrams.
If I could chime in, it seems almost as though the 4 strands are kind of like the 4 possible linear combinations of 2 columns if you think about the symplectic form. Like you can have just the X part, just the Z part, both and neither.
Mm-hmm.
And then the action of multiplying by an X or a Z will properly, I guess, negate some of those columns, the ones that have that term present. And then the H's and the S's will permute them in some way, as will the C naught on two of those things. So I think using that as an intermediate between something more familiar to purely quantum people, like the symplectic form of something like a stabilizer tableau or whatever, and these four wide strands can probably sort of resolve the conversation
I
about
see.
which things can be generated by what other things.
I see. Yeah, I haven't thought about it that way, but I think it's a good insight. Thanks.
Yeah, thanks. I think that helped with the intuition.
Okay. Thank you.
Sorry, I have another question. So first, your Hadamard gate is not self-inverse, right?
Oh, sorry, my Hadamard gate is what?
It's not self-inverse, right?
Self-inverse. Oh, no. I didn't present, but like, this is self-inverse actually. There's a diagrammatic rewriting rule that I can employ so that you can make it a parallel four lines.
Okay, so if you combine two H's, you have additional writing rules allowing you to go back to identity.
Yeah. So that is not directly followed from the diagrammatic identity that I presented earlier, but there are diagrammatic rewriting rules that you can bring those seemingly complicated looking like braids between four lines into the four parallel lines.
Okay, and second question, you said before that you are not in a monoidal category, meaning your black dots, they do not commute. So what is the formal definition of two black dots side by side? Because it's ambiguous, right? If you put
Yeah, right. So I didn't present this either, but four lines means that this is I gamma 2 gamma 3, for example. So I multiply additional phase factor I, and this is like just a diagrammatic notation makes it everything easier. Oh, so Leah sent diagrammatic rules in the chat, so you might want to check that. Yeah, thanks for the screenshot. Yeah.
Okay, thanks.
Okay, so any other questions? If not, I can move on to the Matchgate or diagrammatic characterization. So Matchgate tensor network can be represented by a Quon diagram satisfying two properties. The first property is which we call boundary tracking property, and the second property is the whole free background manifold. So the second property is easy. If you look at the background manifold, then there is no hole or genus in the diagram. And I'm going to explain what I mean by boundary tracking property. So boundary tracking property means the following. So along every boundary of the background manifold, there is a corresponding Majorana lines that just follows through the boundary of the manifold without braid or scatter with the nearby Majorana lines. So this is an example where it satisfies the boundary tracking property and the whole freeness of the background manifold. Also, the proof is easy. From the generating set, you can see that all these Quon diagrams satisfying the boundary tracking and the whole free background manifold property. But if you do the tensor network contraction in a planar way, it potentially have a loop as a tensor network. So for example, let's say each tensor is a Matchgate tensor, but then your tensor network can potentially have a loop as a tensor network. Then if you glue the corresponding Quon diagrams, you will result in the Quon diagram with the hole in the background manifold, which seems to violate the condition B. But because of the fact that you have this boundary tracking property, all these isolated holes always have a corresponding Majorana loop that solely includes that genus and hole. So that using string genus relation, you can remove those two altogether, Hence, the resulting Quon diagram resulting in the diagram satisfies the two properties. Any questions? Yeah. So with that is already powerful enough to generalize a further tractable class that lies beyond the matchgate, which we call the punctured matchgate, where the punctured matchgate is the Quon diagram with only boundary tracking property, like for example like this. And if we fill in the punctures by matchgate with the appropriate size, then all the diagram and the corresponding tensor network reduced to the matchgate tensor network, but only when if I fill in the punctures with the right matchgates. So with that, I gave some like diagram characterization of the Clifford and matchgate using Quon diagrams. And then finally, I'm gonna enter to the application. But before that, if you have any questions, oh yeah, Leah raised a hand, so could you speak up?
Hello, thanks. I have a question about the matchgate part. So in your paper, you give a diagram with 11 parameters for a matchgate, but do you have a form that can be used with 7 parameters, which is the minimum needed? So a 7 parameter form in the ZW calculus was given in, it appears in this paper, but I don't know if that's the first time it appeared.
I
But
see.
do you
So
have,
but what do you mean
if
by
you,
11 parameter? So I don't know. What do you mean by 11 parameter, for example?
on the last page of the PDF I just sent,
Mhm.
I don't know if that's the first place it appears, but it's the first place I know of it appearing. They have a ZW calculus diagram which has any arbitrary matchgate in a diagram with 7
Oh, I see.
parameters. But then in your paper, I think you have 11 or something like that. I was wondering if there's a way to translate between the
Okay,
ZW
so
calculus and or specifically the matchgate, arbitrary matchgate.
so I don't think I get what you meant by parameters in the matchgate. Could you elaborate more? So maybe there's some language that I don't like. I'm not very familiar with. So what do you mean by like 7 parameters in that paper and 11 parameters in my paper? Oh, um, are you guys online or hello?
I'm still here.
Oh, okay. So
Yeah, me too.
yeah. So anyone could elaborate our question, or I'm sorry, I couldn't get the
Oh,
understand the gist. Yeah.
sorry, I had muted. Your equation 52 gives a 10 parameter, so 10 bases, Q, 2D Quon diagram for a 2-qubit computation where every gate is a match gate.
Mm-hmm.
Or sorry, that's a 4-qubit computation. Do you have a diagram that can represent arbitrary 2-qubit match gate? With so most general would be 7 parameters. There's 8 total map parameters in the matrix, but it's possible to do
Yeah.
with 7
So
parameters, like in the last figure I said.
okay. So I think the has chat like Rajin sent like this 2-qubit match gate of the following of 2-qubit match gate, and I think there's like an additional determinant condition that needs to satisfy in order that gate to be a match gate, right?
Yeah, that's
So
correct.
that's what you meant
And
by 7 parameter.
yeah, because of the determinant condition, it's possible in ZW calculus to get it to be a 7 parameter diagram. It's the last figure of the very last diagram of the link I sent.
I
And I
see.
wondered how to translate that into the 2D Qn language.
So I only briefly did the calculation in the appendix on my paper, but I think the parameter-wise, it should be the same. It should be the 7 parameter in total if I did it in a clever way.
Okay, I'll look at that.
Thanks. Yeah. So my understanding is that like we are representing the same Matchgate tensor, so the parameter-wise, it should be the counting should be the same. Okay, so with that, let me. Any further questions, comments?
I guess this is the same as the previous proof, but do you have an intuition for the opposite implication? So
For
like
example, the
given a
Matchgate
Quon
diagram.
diagram with these properties, they can
Yeah.
always be written as a Matchgate diagram.
Oh yeah, it's the same as previous Clifford proof. You do the diagrammatic parsing, and so since the diagrammatic element appearing in the Quon diagram is not that many, you can present all the possible dictionary and then just like do the translation by looking, oh, this portion of this part of the diagram has to map to, for example, Z rotation. This portion has to map to XX rotation. You can always do that.
Yeah, thanks.
Thanks. Yeah, if there's more questions, then in the remaining 10 or 15 minutes, let me present the application. So I'm reusing my first slide that's saying that tensor network is interesting and exciting, but there are challenges such as the contraction, how to make a contraction order, what are the solvable or tractable cases, and how to quantify, for example, magic resources. So in the 2D Quon diagram, it provides a way of characterizing magic resource. For example, this diagram violates both the diagrammatic characterization for Clifford and Matchgate. But when I view this diagram as a diagram that violates the Clifford diagrammatic characterization, then the non-Cliffordness coming from the number of scattering elements in the diagram. And instead, if I view this diagram as a diagram that violates the Matchgate diagrammatic characterization, then the number of holes gives the way of giving the measuring magicness of the diagram. So it sort of gives an efficient recognition of the low magic states. And hopefully we can use Quon diagrams to do the resource optimization, such as further reducing the T-gate count. I guess this kind of optimization has been used using GX calculus, and I really hopeful to learn those kind of techniques or tricks that has been used in the GX calculus, and whether it can or cannot be applied in the Quon setting. And also, I'm going to present the tensor network decomposition theorem, which is presented in our work, which says that any tensor network can be efficiently. Oh, so KH raised his hand? Oh, no.
Hi.
Okay.
Hi. Sorry, is it possible we go back to the previous slide?
Yes.
How can I view this as like so if I look at a Quon diagram,
Mhm.
what is the total amount of like magic in this diagram? How can I is there into it? Well,
Yeah. Just count the number of scatterings, for example, for the non-Cliffordness, and count the number of holes in the non-matchgateness. So the way I say this is the following. So let's say I view this as a non-Clifford diagram with the violation being the number of scatterings. Then using the diagonality rewriting rules that I presented earlier, which is like maybe not the rewriting, but the diagonality. So you can expand the scattering, you can replace the scattering element as a one parallel line plus another parallel line with dots in it. So you can let's say you do all this substitution for individual scattering elements, then you make a superposition over 2 to the number of scattering diagrams where each of which is Clifford and efficient to contract.
okay. Thank you.
Yes. Thanks.
Here for the non-matchgateness, do you also need to count the non-boundary tracking?
Here
Value?
no. Here actually no. You can also expand. So I didn't present all the details, but essentially you can replace all the number this non-matchgate diagram as a superposition of matchgate diagrams, each of which is allows of matchgate computation. And then the number of terms is given by 2 to the number of holes. Yeah. Okay, so any
Can I ask
question? Sure.
sorry. Can I ask, is it necessarily the case that the number of holes is equal to the number of failed non-boundary, like non-red lines? So in this
No,
example it is, but is there any relation?
no, there's no relation. Generally, it doesn't have to be the case. Here, it just happens to be the case. But I'm just saying that like number of holes is the correct, is one way to measure non-matchgateness. The boundary tracking property is in some sense is not necessary. Okay, so if there's no other question, let me move on to the tensor network decomposition theorem. So decomposition theorem tells me that any tensor network can be efficiently expressed as a tensor contraction between single Clifford and single Matchgate tensor. So for example, if you give me some very complicated tensor network with non-local connectivity, non-planar, all the tensors are very complicated and so on and so forth, I'm saying that I can efficiently compile into the tensor network, tensor contraction between single Matchgate and single Clifford tensor. And I should say that this compilation process is efficient. And then I defer all the potential hardness in the computation as a largeness of the bond division between Matchgate and Clifford tensor. And as I said earlier, I assume the tensor network, the tensor leg is always a qubit tensor leg. So if you have many tensors between Matchgate and Clifford tensor, that gives the like a large bond dimension between the two. So the proof, I'll just, oh, okay. So there's a hand by KH, yeah.
Hi, sorry. What is the relationship between is there any functional relationship between or like a rough functional relationship between the how large this bond dimensional is?
Functional, oh, what do you mean by functional relationship?
So well, you said large. What is how large is in general? In some like
In
for
general.
example, yeah.
So that depends on the tensor network, initial tensor network. But in the paper, we give A algorithm to reduce arbitrary, given a tensor network, we give A algorithm to reduce to this form. But this form is not unique. There could be another like tensor network which is the same but has the small bond dimension, for example.
I see. Okay, thank you.
Yeah, I'm just presenting a way, and then let's say you have this form, then what you can do is that you can do the brute force computation by doing all the superposition over all the possible bond dimension between the two, for example.
Sure.
That gives the like upper bounds on the computation complexity, for example. Yeah.
I see. Okay, thank you.
Yeah, thanks. Yeah, so decomposition theorem is I'll just highlight the proof where first observation is that any tensor network can be expressed as a planar tensor network using the swap gadget. When there's like a non-planar connectivity between the two, I can replace that by adding a swap gate. And then use the concepts from punctured matchgate, you can prove the decomposition theorem, which I will not present in this talk, but you can find more details in our paper. Any questions? If not, let me move on to the final application, which is a variation ansatze. So as we know, we want to use some classically tractable states to solve some many-body or some optimization problem. For example, you can try to use Clifford state to solve some many-body, use as a variation ansatze. It has a nice property such as it has multi-body correlation and is tractable, but it has no continuous parameter and hence it's difficult to optimize in general. Instead, you could use Matchgate to use it as a variation ansatze. It has a continuous parameter. It's easy to optimize. It's also free, so it's tractable, but it does not contain any multi-body correlation, and we want both. And we've presented several ansatz in our paper, and the first ansatz, which I call ansatz 0, is a hybrid Clifford-matchgate-MPS. This is a tensor network arranged in an MPS type of geometry where each tensor could be either Clifford-matchgate or low-rank tensor. But I'm gonna keep the bone dimension between closed tensor legs remain small. But the number of open tensor legs of either Clifford-matchgate can be large. More generally, trace tensor network type of arrangement is possible. And it is also motivated by our tensor network decomposition theorem by demanding that the lowness of the bone dimension between these tensors, then the resulting tensor network is classically tractable. But we presented this ansatze also in order to also because this simple looking tensor network captures the tractability behind certain class of non-planar diamond model. Any questions in between? If not, let me move on to the punctured matchgate. So I gave you the diagrammatic characterization of punctured matchgate, but there's an equivalent way of characterizing the punctured matchgate as the following. The punctured matchgate is a tensor. It can be obtained which can be obtained by a non-neighboring but planar contraction of a matchgate tensor. So in this case, I have two punctures, but it is strictly larger than the matchgate class, and it generally represents the non-Gaussian state. The punctured matchgate is tractable in the following sense. The computation of each component is efficient. If you give me a bit string of individual tensor leg, then the computation of that is efficient. So this alone allows to do the Markov chain Monte Carlo simulation, which is routinely used in the variational Monte Carlo in solving quantum many-body problems. But I should note that computing the normalization is hard in general, which scales exponentially with the number of punctures. Any questions here or? Timing wise, is it okay if I go slightly beyond like 10?
Yeah, that's fine. I mean, if people have to go, they can go. So.
Okay. Yeah. So let me just continue then. So since our paper, we have a better understanding of the punctured matchgate. So one way to get punctured matchgate is through some gadget construction. For example, if I have a matchgate state and I can apply punctured matchgate unitary to get the punctured matchgate state. So here, this part is a punctured matchgate unitary. So if you look at it, this is like an XX rotation, but non-neighboring XX rotation. So applying this unitary brings you out from the matchgate manifold, but we are applying the unitary in a structured way so that the resulting state is still tractable and lies within this punctured matchgate framework. We can apply some deep circuits on the matchgate circuit or on the matchgate state in a more structured way. And this becomes a punctured matchgate if I push the tensor legs into the correct positions And this tensor network now become a planar match-gate tensor network with punctures. In this case, have 7 punctures. And nice thing is that since I'm applying some unitary operator, unitary gates on the normalized state, the resulting punctured match-gate state is normalized state by the construction. And it has an efficient, you can prepare the state efficiently in a column circuit, for example, although it's non-Gaussian and so on. Yeah, so I'm working with some quantum chemist group to use this punctured match gate as a variation ansatze, and it's like checking what's the performance of this ansatze and so on. And finally, oh yeah, Leah have yeah. Sure.
Can I ask a quick question about your punctures, these orange highlighted parts, when those
Yeah.
lines disappear, either entering your match gate or what does it mean when they disappear? How is that interpreted?
So disappear meaning that here is a tensor lab, but it just like stops here.
Yeah.
Yeah. So as a quantum circuit diagram, you would imagine something like this. You always have at each time slice, you always have an n-qubit state, right? And when it comes to tensor network computation, for example, if I ask you, oh, given the state represented by this quantum circuit, let's say I specify all the bitstring configuration of the open tensor leg, I can ask what is the corresponding quantum amplitude. And when you do that computation, you can move these tensor legs inside the punctures and view all the tensor network as a planar tensor network contraction. Then it reduces to the match gate computation, which is efficient. So that's what I mean by like having punctures and pushing the tensor legs in the puncture and so on.
Cool, thank you.
Thanks. Yeah, so finally, I'm gonna present the ansatze that generates like a huge class of tractable class using our Quon diacritic moves. So far, the previous ansatze, we don't really use Quon to get those tractable ansatze. But for this one, we are explicitly utilizing all the Quon diagrammatic rules and diagrammatic rewriting moves. So for example, starting from some tractable tensor network, which is like a tensor network represent the Clifford tensor network, I can use a series of diagrammatic moves to generate a very complicated tensor network, which is still tractable by using 3 moves. The first one is which we call inserting, where given a tractable tensor network and its Quon diagrammatic representation, I insert some, say, closed Majorana diagram or some string hole pair in the diagram. As it is, it does not change. It does not essentially change the contents of the tensor that is represented by the diagram, because I can always undo this diagram to move to get back to the original diagram. And the second move is which we call stretching, where we stretch the strings either to the inside the bulk of the diagram or even outside the Quon diagram. And for the lines that lies outside the diagram, we cut these lines and generate a new open tensor leg. So by doing so, we introduce additional tensor legs in the diagram. So now the tensor contents of the tensor network represented by a Quon diagram is completely changed. The final move is called switching, where we either switch the braid type, or given a braid, we change that by an arbitrary scattering element. But the latter one increased the computational complexity, so we'd better use the latter move in a controlled manner. But this restriction is in some sense very natural, in a way that if I allow some arbitrary number of this last move, then starting from the I can generate arbitrary tensor network diagram using by combining these 3 moves. So there's one move that you need to restrict, which is this move. So here I present the diagrammatic ways to generate some large class of tractable states with high non-Cliffordness and high non-matchgateness. And there's no obvious geometric separation between Clifford and Matchgate part. So as I said, I utilize the three diagrammatic moves: inserting, stretching, and switching, where the first two does not increase any computational complexity, and the third one potentially increases computational complexity, but in a controlled way. And I should say the first two are already enough to generate entire class of punctured match gates, starting from the trivial Quon diagram. Yeah, do you have any questions? Yeah, if not, let me just highlight the Kramers-Wannier duality and end my talk. So in our paper, we derived the Kramers-Wannier duality using Quon language, where the Kramers-Wannier duality amounts to having the following identity of the following partition function of the Ising model. For example, you have an Ising model with a square lattice, and your spins lives on these vertices of the lattice, and then you have an Ising interaction between nearby sites. Then you can rewrite it as a matchgate diagram, tensor network diagram, and the corresponding Q1 representation looks like the following. And using the string genus relationship and also some what we call spacetime duality of the scattering element, we can rewrite the tensor network as the following form. And then by grouping in a proper way, then it gives the partition function of the Ising model in the dual lattice, meaning that the Kramers-Wannier duality of the classical Ising model in the 2D lattice. With that, let me conclude. So we introduced 2D Quon diagrams and show the universality results, and we present some diagrammatic characterization, Clifford-matchgate, and based on that, we present the generalization into something we call punctured matchgate, and we discuss various applications in the tensor network and then the various answers. With that, thank you very much for your attention.
Right. Thank you very much, Byungmin. A nice
Yeah,
talk.
thank you. Any questions or comments?
Yeah.
I would like to hear some more comments on the GX community, GX calculus community.
Hello.
Yeah.
So thank you for the nice talk. In fact, it's
you.
resonating with a lot of things that happened recently with the Matchgates and Clifford, and also fermions using ZX-like techniques. So my question, I would like to make link between this and ZX style diagrams. My main problem here is that I don't really understand the semantics of your diagrams, the definition at the very beginning. Could you explain what is... So usually what we do is that we explain what is one wire, because then the objects, and then we have to explain what's the meaning of composition, and mainly here, I think the most important part, what's the meaning of putting two things side by side? Mathematically. Because here it's not tensor product, clearly not.
So like two things side by side mean the A tensor here and B tensor here with like this.
Tensor commutes, and here you have, when you tensor two maps, it's always commutes. And here your black node, they are not commuting. So it seems you're using something else that tensor products for.
Yeah. So the point of this like blue shading and like this Quon diagram is that with that it commutes. So I'm intentionally using like two dots appear in this like same height and use a separate diagrammatic notation.
Yeah, but I mean, you have a positional framework, so you also have to have a proper mathematical definition for your elementary components, right? So you cannot dodge the question by saying when they are 2 by 2, it's okay. I would like to understand what is the mathematical definition of one wire and what happens when I put two wires side by side.
So what do you mean by one wire? One wire meaning this line or like
Yes, this line,
pair
so
of
the
or
black one, the black line.
one blank line.
So it's supposed to be a vector space, I guess.
So okay, one wire, one black line alone cannot define the valid Hilbert space, but it has to come with even number of wires. If so, then you can associate the corresponding vector space or Hilbert space.
So for you, one wire has no mathematical meaning, in fact. It always comes with
Right.
something else.
It has to be even always.
So you cannot define what is one wire and how to compose wires. It's not like it. You're not in a compositional approach when you can decompose everything to elementary components.
Yeah, then I need to do like quartet of Majorana lines, quartet of black lines.
Okay. So then for you, it doesn't make sense to ask what happens when I have two wires side by side. Because it has no meaning to you.
Yeah, like for example, I in the diagram I can have like two wires like this, but because of the parity even projections that I impose, these represent only one-dimensional Hilbert space, which does not really encode any meaningful quantum like states. So because of that, you can always do this kind of diagrammatic rewriting by changing the connectivity of the manifold, for example.
So if you come back, you have an equation at some point when you put two black nodes in a row and it equals the identity, right? Can you come back to this slide?
Oh, yeah. So this one.
Yes, but what is the mathematical meaning of this if you say to me that one wire doesn't mean anything? It's not a...
Oh, yeah. So here there should be some other black lines in order to make this like sort of
Okay.
even
So
number of wires. Yeah, right.
Okay,
You're right.
I see. Okay. So there will be a lot of work, I think, to make the languages match. But thank you.
Oh, I see. Yeah, it's good to know. Thanks. Yeah. But my understanding is that if I just use like those parallel dots, then like moving these parallel dots between the two does not give additional like sign factor, so you can just move it around.
Yeah, this I agree. Two by two, I agree. And in things you can even give a mathematical meaning to that, right? Because if you have two wires, can you make an Hilbert space?
Yeah, but it's one-dimensional Hilbert space, right?
Okay.
You can do that.
And
Yeah.
then you could show it's tensor prudent. Okay, I see.
Is it only one dimensional if you put the background, because then you're projecting into the even subspace?
Yeah, exactly. Yeah.
But if you don't have that background, then it is a two-dimensional Hilbert space. Is that right?
That is also true. Yeah, that is also true.
So if you remove the blue part, then two wires gives you like a qubit.
But I'm working
figure.
on this 2D Quon diagram, which requires this blue background. So I'm always, in a way, I'm always demanding the blue background to be there.
Yeah, but if you do it like step by step, where we just give a semantics to wires without the blue background, and then later add the blue background, then
Oh yeah, you can think of that way. Yeah.
so then the two wires are a two-dimensional space.
Yeah, exactly. Then the wires are meant to encode like two-dimensional Hilbert space. I agree. Yeah, Leah raised her hand. Could you speak up?
Yeah. Is there always a way to take any sparse encoding diagram and write down the corresponding to take any dense encoding diagram and write down the corresponding sparse encoding diagram? So going the opposite direction doesn't work because you can't express swaps in the dense encoding. But is it necessarily the case that all dense encoding diagrams you can always write it down in a straightforward way, or is there any challenge?
I think it can be done easily. So what you're saying that so dense encoding, like say 0110 or something like that, you can always use that say qubit and embed into like parity even of the two qubits. So at the expense of like having like say n qubit state to like two n qubit states, you can always do that.
Is it really straightforward? Say you've got some really bundled like a lot of swaps and a lot of like fermionic crossings and you've got this really mess of a lot of wires crossing over each other? Or is it always that easy to take any piece of the wire crossing or holes and get
Yeah,
it
yeah.
from dense to sparse?
So the rough way of doing that is that you insert string genus relation on every like so let's say you have very complicated like minor lines. What you can do, you can group like two Majorana's and every other even Majorana's you insert like string genus relation properly so that you make a quartet of Majorana's in between. That's the very high level of idea.
Oh, that's really interesting. Thank you.
Hmm.
So I'm interested to know like what the data structure here actually is. So for a ZX diagram, for instance,
Mm-hmm.
the way we implement this in code is like we save it as a graph with nodes and vertices, with like special boundary nodes to determine the inputs and outputs. But here it sounds like you need a lot more information on your structure because you have an ordering on like time and you have
That's
this
true.
thing with holes in it and you have a boundary. Like what's the data structure here?
Yeah, that's a very good question. Then also I also wanted to implement correct data structure and like possibly code up. I'm not sure. So like at the very high level, this is like a nothing but an knot diagram. So in a way, using this kind of knot diagram encoding, you can sort of do this. You can sort of encode the Quon diagram into some so proper data structure. But care must be taken, and I don't know. Like I haven't really like worked out like step by step details. But I'm very curious to do that.
How do you make those drawings? Perhaps that could
Oh,
help.
so how did I draw this diagram? So I use TikZ, TIKZ in LaTeX. Yeah.
But so I'm talking from the perspective of a programmer, not somebody that actually understands the
Oh,
physics involved. So do you actually like move the lines manually, or are they directly extracted from, let's say, an equation or a data or a string or something?
could you elaborate more on your question?
Yeah, so in the program that you use, I'm trying to
Mm-hmm.
like follow up on the same question of the data structure. You produce this using that program, but like, do you, let's say when you're making it, are you moving the lines like with the mouse, or is the picture generated from an equation, a string, a tensor? Where does the
Oh,
picture come
here,
from? And yeah.
like in like when I write the paper and generate all this plot, I literally use like TIKZ, TIKZ. So I I specify all the connectivity between lines and then like draw lines based on that. But yeah, but it is slightly different from the data structure you would want to encode, like you would want to implement using computer programming, for example.
When you say that you specify the connectivity between the lines, does that
Yeah,
mean
yeah.
that you are using actually graphs, but we don't see the nodes in here?
Yeah, for example, I'm gonna draw lines connecting this particular point and that particular point with some angles and with some tension, and that will give the line, for example.
Okay, all right, that's very interesting. All right, cool.
Thanks.
I just had a question about your sort of obfuscation methods to produce
Oh, yeah,
these
yeah,
hard
sure.
to simulate tensors.
Yeah.
So I think what you're arguing, right, is that
Hmm.
you can create these tensors which look very hard to simulate, but
Yeah,
they're
yeah,
actually
right.
easy to simulate because they are within these rewrite rules of something that's easy to
Right, right,
manipulate.
right,
Is that correct?
exactly. Yeah,
So
yeah,
if
that's the
I,
rough
hmm,
understanding, you're right.
yeah.
Yeah, for example,
And
right,
so are you
yes.
arguing that therefore this method is more powerful because it can simulate these complicated things that other methods can't simulate?
Probably I'm not arguing that very strongly, but I'm just saying that there's a way to generate a tractable tensor network, which is not obvious if you just look at the final output. And maybe it can be used as an obfuscation. That part
Yeah.
I'm not sure. It could be that there is like a secret structure in all the set of diagrams that are generated through this process, which is in fact easy to simplify even without using these complicated diagrammatic rules. That I don't know.
Yeah, because also if you were to be given this obfuscated thing, it would not necessarily be obvious which rewrite rules you need to apply to it to get the efficient simulation.
Exactly. Yeah,
Yeah.
so that's a trick. Yeah, we need to know how it actually evolved through this diagrammatic moving process
Yeah.
to going back to the original diagram.
Mhm.
Yeah.
Yeah.
So in the GX calculus, using GX calculus, is there like a results on obfuscation?
So I know there is this work in circuit diagrams on
Mm-hmm.
doing unoptimization, what they call it. Like they deliberately
Mm-hmm.
make the circuits more complicated, and then
I see.
they use this to benchmark existing optimizers to see if those optimizers can undo the
Oh, I see.
obfuscation. And in
I
many
see.
cases, they can't undo the obfuscation because obfuscating is so much easier than optimizing. So,
I see. Makes sense.
Miriam, do you want to say something about this?
Yeah,
Yeah.
it's sort of an obfuscation thing using ZX. There's this paper about blind quantum computing.
I see.
So it uses measurement-based quantum computation, and the idea is, yeah, to kind of send your computation to servers, like split it between two servers, so that if
Mm,
servers don't communicate, they won't learn anything about your computation.
mm,
There are standard protocols for that, which yeah, kind of are independent of the specific computation you want to do. But there's one paper by I'm blanking on the name now. Someone from Oxford Physics, who kind of showed that there's a way of doing it in a more resource limited way by
mm.
using ZX calculus to basically take your starting computation and rewrite it in such a way that it becomes obfuscated.
I see.
So it's a slightly different, I guess, perspective.
Mm,
But
mm,
it kind of goes in a similar direction.
I see. Yeah, thanks.
Yeah, that